Hello students and welcome to another video. I'm your teacher Mr. Flynn, and today we're going to be talking about periodic table and atomic structure. So we're going to go a little more in depth than we did last time, because last time was more of an overview of kind of like how the tables are arranged and organized, but now we're going to talk about why they behave as they do and why they are stacked the way they are in the table. Okay, now let's look at this table down, or this diagram down below. Okay, you can imagine the periodic table is of 4 blocks. You have S, D, F, and P. The only 2 I really care about, especially in this class, is the S and P. And we call those element groups the main group elements. They're the ones that we're going to spend the most time talking about in this class. And this diagram goes into detail and it starts to show you the electron configurations of these main group elements. So if we look here, you can imagine that lithium has 3 electrons, and how those electrons are arranged. Okay, it has helium as its noble gas configuration. That's our checkpoint. And then now that we're in a new period, we're going to start counting up the electrons in that period or energy shell. Okay, and this has 1 electron in its valence shell, so the 2s orbital. And then, but we know that the s orbital can hold 2 electrons. So beryllium, its second electron will actually hold that second electron because it's got 4 electrons total. So 2 of them will be in the first energy level, and then the second set of electrons will be in the outer shell, okay, the valence electrons. All right, and we learned how to draw these last chapter. Okay, now it tells us a lot that there is 2 electrons in this valence shell, because the valence electrons are the electrons that are doing the interacting with other atoms. Right, they're the ones that are on the outside. They're the ones that are making contact with other elements. Right, and for example, lithium and beryllium, they have a really hard time holding on to those electrons, and they actually get taken from them. All right, and they form ions, but we'll talk more about that later. But the idea here is that they are reactive because they can't hold on to their electrons. Okay, because it's a big shell, right? Because you also have the p block that's also part of this energy shell. And let's look on the flip side. We have fluorine and neon. Right, its s shell is full, and the p orbital subshell is got 5 electrons in it, and then neon has all 6 electrons filled in the p subshell. All right, so let's look at neon, for example. Okay, we have helium, and the s and p are full. This neon has its entire shell full, right, and it doesn't want to gain or lose electrons because it's happy and content with what it has. Right? It doesn't want to lose electrons. It doesn't want to gain electrons because it's all filled. While fluorine, it has a missing spot in its p orbital because it can have 6 total, but it only has 5. So it's going to most likely steal electrons from other atoms. So that's why fluorine is reactive, because it wants to fill that p subshell. All right. On the left side, they're reactive because they want to give away their electrons, and on the right side, they want to take electrons from other atoms. That's why they're reactive, because on the outer, the valence electrons are wanting to take and steal from each other. Okay? All right, now let's go through and describe how it is that electrons and how they give and take electrons. Okay, we'll talk a little bit about that here. Okay? Let's go to the side of the page. All right, now this is an example of sodium. Right? We have neon, that's our checkpoint. All right, so noble gas configuration. And then 3s1. So we're now in the 3rd energy level, and we're in the s subshell, sphere-shaped, and it has 1 electron in it. All right. So sodium, it's got 11 electrons. So 10 of them are in the blue box, because we can fit 2 and we can fit 6 inside. So these are called core electrons. If they're inside in this blue area, they're called core electrons. If they're on the outside, we call them valence electrons. And this one only has 1 electron, and it's in the 1s orbital. Okay, so let's imagine core electrons and valence electrons. Okay, before I use this example again and talk about what's going on with the electrons interacting, let's talk about Coulomb's law. I want you to write down this definition. Okay, it tells us that the strength of the force between 2 charged particles, the Coulombic force, depends on the charge of each particle and the distance between them. I don't need you to memorize this equation. We're not going to be working with this in the class. But I do need you to understand what the trend is. What is happening between charged particles? So here we have our kind of control, our basic example. We have a positive and a negative, and they're attracted to each other, and they're moderate sizes, and they're at a moderate distance from each other. Now what happens if we change the charge? What if the charge on this positive one gets more positive, and this one stays the same as negative? Well, they're going to feel a greater attraction to each other because one of them has more attractive forces. Can you see these arrows, how this one's bigger, right? So the size of the charge will increase their attractiveness to each other. Their ability to pull in and be closer will be greater because of the size of these charged particles, this one being bigger. Now, also what's affected is the distance. If they're farther apart, they will feel less pull from each other. All right, so if they're separated and if they have moderate charges on them, they will feel less of attraction. Now, what would happen if I increased the size of this one and made it look like this? Well, the attractiveness would increase, but it wouldn't be as good as this one because they're farther away. Now, you may ask, well, what would cause charged particles to be separated from each other? Right? Now let's look at this diagram. Okay, we've got our core electrons on the inside, and on the very outside we've got our valence electrons. So let's take some time and just appreciate kind of what all these arrows are representing. So we've got our first two electrons. They are being very attracted to the nucleus because they are close, and the charge of the nucleus is much bigger than the individual electrons. Like these are both -1, -2. This nucleus can have a +11 charge, right? So it has a lot of protons in here giving off a charge. So they're going to feel really attracted and then be pulled very close to the nucleus. All right, now on the second energy level, okay, these three electrons, they're being pulled in because they're relatively close compared to the valence electrons, but they're also being repelled a little bit. They're being pushed back by these inner core electrons. Okay, they're actually getting a little bit of pushback. They're being pulled in, but they're giving a little bit of pushback from the inner ones. Now we get to the very farthest electrons, and now these ones are the farthest away. See how that arrow gets really skinny compared to this arrow? It's because the attraction is a lot harder to feel because they're farther away, and you have all these electrons inside pushing them away. All right? The only thing that could change its ability to be attracted to the core or being attracted to the nucleus is the size of the nucleus. And we'll actually talk about that trend, effective nuclear charge, here in a minute. Okay? But the idea here is that electrons are all pushing off of each other, and the only reason they're being held together is because there's a large charge in the middle. And sometimes this charge in the middle is not enough to really hold on to these electrons. And sometimes the charge is big enough that it can really hold these electrons in, and it may even want to take another. Okay? So this is called the shielding effect. The shielding effect is the core electrons are shielding these valence electrons. And these valence electrons are the most vulnerable because they're the ones interacting with other atoms that are coming close to it. Right? If we imagine there was another nucleus like this one, or another atom like this one next to it, then you can imagine that these valence electrons would be interacting with each other. Are they going to want to be taken because they can't be held onto? Or is the nucleus big enough that it's actually able to keep and actually steal other electrons from other atoms? All right, so there's these Coulombic forces you got to be aware of. The size of the charge and the distance are what determine how well an electron and a protons are attracted to each other. So let's talk about effective nuclear charge. This is a very important aspect because we're going to use this to describe everything about periodic trends in the next chapter. So you need to understand this. There's a simple formula for this, and you need to understand this. So the effective nuclear charge, this is the symbol for it, ZF, all right, is the number of protons, Z, minus the shielding constant, S. So S is actually going to be your core electrons. All right, so we have our number of protons, the number of protons minus the shielding electrons. All right, now let me give you an example of this on the next page. Okay, you'll see there's a trend here that the effective nuclear charge increases from the left to the right side of the periodic table. And let me explain why. So if you look here, we have sodium, magnesium, and aluminum. They're all next to each other in period 3 of the periodic table. And as you work your way across, the effective nuclear charge increases. So the idea of effective nuclear charge is that it's the ability of the nucleus to attract and pull in those outer valence electrons. Okay? It's the feeling that these electrons feel. Is that part of the definition on this? It should be. It is the net positive nuclear charge experienced by an electron of an atom. Oh, all right. But the main idea that I want you to take away is that the feeling, the pull that electrons feel from the nucleus, it is actually what a effective nuclear charge is. So for example, we have Z minus S, which is 11, because we have 11 protons, and we subtract 10 because we know that our noble gas configuration, neon, represents the core electrons. So there's 10 electrons in neon, okay? So 11 minus 10 is plus 1, or 1 plus, all right? That's how this electron on the outside feels that pull in towards sodium. Now let's look at magnesium. It has now 2 electrons in its outer shell, but the difference is magnesium has another proton, meaning the nucleus and the charge is greater. But you think, well, there's another electron in here. Is it going to be spread out? Well, you got to think that the only thing that's affecting the pull of these electrons on the outside is the core electrons. So sodium, magnesium, and aluminum all have the same number of core electrons, but the size of the nucleus increases from magnesium to aluminum because this has 12 protons, this one has 13 protons. It has a bigger charge, and they're all overcoming the same number of core electrons, so the feeling that the electrons on the outside feel is greater as you work your way across. So this one has 12 protons, and we subtract the same number of 10 core electrons, because there's the same across all 3 of these, because they have the same number of core electrons, is plus 2, because the nucleus is bigger. Now aluminum has a bigger nucleus, and it has plus 3. And you can do this all the way across until you get to argon, and argon is going to have the greatest effective nuclear charge. Its ability to pull in and hold on to all 8 of its outer electrons is the greatest because it's overcoming the same 10 core electrons, but it has a much bigger nucleus. So actually the size of the atom shrinks as you work your way across the table. That's one of those trends that we'll talk about in the next section. So please take some time to appreciate this. I want you to draw this in your notes and draw this arrow showing effective nuclear charge is increasing. And I want you to demonstrate and understand why it is that the ability for the nucleus to pull in these outer electrons increases as you go across the table. All right, and that's because the size of the nucleus is bigger, and it can overcome those 10 core electrons better than it can sodium and its 10 core electrons. Okay? All right, that's about it for this chapter. Please understand this before you watch the next video. Okay, if you're having questions, come talk with me and I can help you. All right? Thanks again for watching. Until next time.